This is the fifth and last lecture on the gas laws. This one's going to be on odds and ends. And the odds and ends we're going to be looking at are non-ideal gases and the boiling point. Let's start with non-ideal gases. And we know that the ideal gas law is PV equals nRT. This makes a couple of assumptions because it's based on the kinetic molecular theory. And this is that gas molecules have no volume, they are point charges, and that no intermolecular forces exist between gas molecules. These assumptions are valid at high temperature and low pressure, but they begin to fall apart at low temperatures and high pressures. If you graph the pressure times volume versus the pressure, for an ideal gas, you should get a straight line. If you take a real gas and do the same type of graph, you get something that looks like this. Why the difference? Well, it turns out that the two assumptions really aren't valid. There can be intermolecular forces between gas molecules, and gas molecules really are not point charges. And this is calculated using the van der Waal equation. I'm going to show you the equation. You don't need to memorize it, you don't need to use it, but you need to know about it because it takes into account a couple of things. Here is the equation, and the addition to the pressure value takes into account intermolecular forces, and the number subtracted from the volume takes into account the fact that the charges are not point charges. The larger the gas molecule, the less ideal the gas behaves, which makes sense, because the larger the molecule, the larger the electron cloud, so the IMF will be greater, so it would have effect further away from the gas molecule, and the larger the molecule, the less like a point charge it acts. And the van der Waal equation takes that into effect. And it's because there are IMFs, especially at low temperature or high pressure, that gases can condense. If there was never any intermolecular forces, you couldn't go from gas to a liquid. So that's a quick discussion about non-ideal gases. Let's move on to the boiling point. Let's just start with a pan of water that's just open to the atmosphere. That's an open system. And we know that if you leave water in a pan, it will evaporate. In a particle diagram, it looks like this. If you look at the Maxwell-Boltzmann distribution, the kinetic energy of the molecules and the percent that have that energy, the yellow line represents the kinetic energy a molecule has to have to break the intermolecular force and go from liquid to gas. And at 300 K, there is a certain amount. If you raise the temperature, you see that the area under the orange curve is greater than the area under the red curve, which means you've got a higher percentage of molecules that have enough kinetic energy to form a gas. So now, if you take that pan of water and you put on a cover, you now have a closed system. There will still be molecules that can break away and form a gas, but at some point you'll have enough gas molecules that some of them will begin to condense. And when the rate of evaporation equals the rate of condensation, that's called equilibrium. And at that equilibrium, you'll have a certain gas pressure. That's called the equilibrium vapor pressure, and that is specific for a temperature. Think back to when we discussed the vapor pressure of water when collecting a gas over a water. So you can see, once again, going to the Maxwell-Boltzmann distribution, that if I have a greater percentage of molecules that have enough energy go from liquid to gas, the equilibrium vapor pressure should increase as I raise the temperature. As I raise the temperature of any liquid, the equilibrium vapor pressure increases, and when the vapor pressure is equal to the ambient pressure, the pressure pushing down on the surface of the liquid, now bubbles can form, and that's when we say that the liquid is boiling. So you can see on the left what evaporation looks like. Because the vapor pressure is less than the ambient pressure, bubbles can't form. When you reach the boiling point, the ambient pressure and the vapor pressure are the same. Bubbles can now form, and what is contained in the bubbles is vapor of the liquid. So we can now define boiling point is when the equilibrium vapor pressure of the liquid equals the ambient pressure on the liquid. And if you graph it, this is for water, you can see that as you raise the pressure, the boiling point of the water increases, and it's not a straight linear relationship. So for example, if you decide to travel here, which happens to be Mount Everest, and you make it to the top, you'll be 8,868 meters above sea level. At that height above sea level, the air pressure is only a third of an atmosphere. If you go to boil water, it'll boil at 68 degrees Celsius. If from Mount Everest you travel here, which is the Dead Sea in Israel, you'll be 416 meters below sea level. The air pressure is a little bit higher at 1.05 atmospheres, and the boiling point of water is 101 degrees Celsius. And all of this can be used for practical purposes. This is an autoclave. In an autoclave, you have water inside the chamber. You put something you want to sterilize within the chamber, you close the door. A vacuum pump engages. It begins to remove the air within the autoclave. As it begins to heat up, the water begins to boil. The vacuum seal is kept constant, and so the pressure begins to build up, and usually builds up to about 2 atmospheres. And at that point, the boiling point is 121 degrees Celsius. If you keep materials there for about 15 minutes, you can kill almost any and all viruses and bacteria. So this is used for sterilization in medical facilities. At the boiling point, the temperature remains constant. The energy goes into breaking the intermolecular forces in the liquid, and because the higher kinetic energy molecules are escaping, you need to raise the kinetic energy of other molecules, and so the energy can only maintain the temperature, it can't increase it. So that ends our odds and ends. So for a quick review, ideal gases are valid at low pressure and high temperature. As you increase the pressure, decrease the temperature, or both, gases will begin to act less ideally. The larger the gas molecule, the less ideally it will act. The boiling point is when the equilibrium vapor pressure of a liquid equals ambient pressure. And no, I have not been lying to you. 100 degrees Celsius is called the normal boiling point of water. That's the boiling point at 1 atmosphere. And while you are boiling, and actually during any phase change, the temperature remains constant. And this ends the section on gas laws. In our next section, we're going to start tackling chemical reactions and stoichiometry.